Give me a time machine for a day. I'll get back to you.
All right. Yep. Anthony makes videos. Here we go. Anna Paulina Luna. For you, I'll throw a lasso around the moona. In a swimsuit, you've been looking real cute. Throw it back, I'm on my way and I'll be there real sooner. Now I'm on an FBI watch list. Don't let them know you watched this on the down low. It's a process. No more games and signs on your secret line. Send me a signal and ask me if you've been on my mind. Open my reply and I'll make you giggle. Girl, you're a 3-course meal, not a feeling to nibble. Aladdin at your balcony, I'm like, do you trust me? I got a special access UAP that goes straight from the sky to under the sea. Anytime, any place, like 1, 2, 3. I got the secret knock, we could stop the clock. I got the key and you bring the lock. No alibi, like tell him that you went on a walk. All the time in the world for when we have our pillow talk. Undock and read one from the book of Enoch. Hit me up cause you're making me swoon up. Anna Paulina Luna. Anna Paulina Luna.
So I was on the naughty list. Per usual.
Bonjour tout le monde. Welcome back. It's been a while. I was focusing on my career, namely switching jobs. No longer working as a software test engineer, nothing wrong with that. But now your boy is officially a scientist. I don't work in tech support. I'm not a consultant. I don't do quality assurance, regulatory, but I'm actually a scientist now. Like, I was thinking to myself, what would my dream job be if not the job that I currently have? So I think a lot about, trying not to F it up, you know what I mean? But the last video I uploaded was the end of reading Differential Geometry by Erwin Kreisig out loud in its entirety for all of you who doubt me out there, who's, when someone says that they read a book, did they actually read it, especially a math textbook? And you can doubt me all you want, and I'll just point you to my playlist with like 40 some odd episodes where I read the whole entire thing. I didn't read the beginning chapters, or not the beginning chapters, like a few of the beginning sections, but 90% of it, 95% of it, probably, I read out loud. So, but when I was first reading that book, I didn't know, obviously, anything really about differential geometry. And some of you can make the fair criticism, like when I got to the critical important chapters, sections, which were on the first, second fundamental form, and then going straight into tensors, the superscript notation threw me off because I'd be like, I'm not sure if it's ds squared or, is that superscript, like a tensor index or something like that, right? So I decided, you know what? I found this problem set doing an MIT OpenCourseware course for computational geometry, which is listed in their catalog as a graduate level mechanical engineering class. But I'm like, I don't know any mechanical engineers who would touch this with a 10.5-foot pole. It's one of those classes, I don't know, you probably don't read them, but I made this post where I sort of explained, I was like, okay, this class doesn't have any exams, okay? It's just like 4 or 5 problem sets, and your grade is entirely what your score is, however many points you get on all these assignments. And the first assignment is basically a crash course in differential geometry. It's just, you could look at it, you can look at my solutions, which I posted on my website, we'll look at that in a sec. It's just like plug and chug, compute first and second fundamental form coefficients, Gaussian curvature, principal curvatures, just over and over and over. But, it's very applied because, they're going to take it and start using it in things like non-uniform, rational B-splines, NURBS curves, whatever. Bezier curves and, get into things like all the different kinds of intersections you could have. Because, right, like in this whole geometry land, the way I see it is there's like 3 or 4 different entities, you could say. There's spaces, you could have volumes embedded in the space. You could think of the volumes in 2 ways. You could have like a solid volume, you could have just the surface of the volume. And that kind of gets to the next one, which is just surfaces. Then you have lines or curves on the surfaces, and then those lines are made up of points. So points, lines or curves, surfaces, volumes, spaces. And a lot of the work that Gauss did pretty much just hit the ceiling, topped off with spaces of 3 dimensions. And I won't go into the whole, general relativity, space-time, you need 4 dimensions, blah, blah, blah. Because obviously the results are very useful and they've been expanded upon since the time of Gauss, right? But to prove the people out there who will continue to doubt me until the end of time and beyond, I decided to do the assignment 1 for the MIT OpenCourseWare Computational Geometry course, which is kind of like I said, a crash course in differential geometry. And the thing is this course was taught in like 2003, and it's 10 problems, and it's assigned on day 2 of the course, and it's due on day 6. So it's like, even if your class is meeting just 2 or 3 times a week, still, if you're going hard at MIT, then, the computational geometry isn't the only course you're going to be taking at a time. You're probably also, doing research, something like that. So, it's a little bit brutal because of how involved the calculations are. So today I'm not going to go over all of my solutions. I'm just going to go over problem 6, which also has like a sketch and illustration portion, but I decided to, take it up another notch and just do it in MATLAB and make plots because, it's computational geometry, right? So might as well code a little something up in MATLAB, right? So if you go to my website here, anthonymakesvideos.com, and you scroll down to files, you can find everything at the top. The first link is a copy of the PDF of the problems. I have my solutions, which of course I typed up, and so I also have the raw LaTeX for my solutions. And if you want to compile it, then you'll also need 3 of these images, which are below here. And then what we're going to look at today is also posted on my website, which is the MATLAB code for these problem 6 torus plots. So here it is in all of its glory, 15 pages of solutions. And like I said, today we are going to look at my solution for problem 6. Let me make sure. I've got to make sure that my camera in camera is not obscuring the text here. Okay, so a little bit more preamble before I get into it. It's basically, we're going to be doing differential geometry on a torus. And the spoiler is that this was already basically covered by an entire section in the Erwin Kreisig textbook. It was section 43 or 44, and it was actually one of the shortest sections in the entire book. It's basically just 1 page long. And in the Kreisig book, it gives you the answers to this problem, it turns out. So if you wanted to cut corners, you're, short on time, you could have just probably copied the answers straight up and gotten a few points, scrape the bottom of the barrel for this one. If it were like a real life, you have to turn in this assignment scenario. But in the book, there weren't actually any work steps in order to achieve the answers. And subtly enough, the U and V coordinate axis directions, which are defined on the torus surface itself, in this problem, U and V correspond to V and U in the Kreisig worked out solution. But anyways, we're going to get into a little bit of like verifying the answer at the very end, I guess. So here's the problem. Consider a torus parametrized as follows. We have a vector r in terms of those coordinate axes on the torus, u and v, and the vector r has three components, the first component being the quantity capital R plus a times the cosine of u closed quantity times the cosine of v. The second entry of the vector parametric representation of the torus is quantity r plus a times cosine u closed quantity times sine of v, and the third and final component is a times sine u, where u is greater than or equal to 0 and less than or equal to 2 pi, and similarly v is also greater than or equal to 0, less than or equal to 2 pi, and in the parametrization, capital R and lowercase a are constants such that capital R is greater than lowercase a. Derive formulae for the Gauss mean and principal curvatures of the torus, and then finally, well, not finally, sketch the torus and subdivide it into hyperbolic, parabolic, and elliptic regions. Finally, in a follow-up sketch, illustrate the lines of curvature of the torus, explain the above subdivision and sketches, and then it was given in the problem statement. This is problem 17 in the book, the textbook for the course on computational geometry, Shape Interrogation for Computer-Aided Design and Manufacturing by Patrikhalakis and Maekawa, which I've got my copy right here. And I actually use this stuff at work as a scientist, developing the scientific software, doing this like CAD CAM stuff in like a multi-physics simulation and all that kind of stuff. So it's actually pretty useful from my point of view. But what we're looking at today is problem 17 from this book, aka section 43, section 4. Well, I forgot which one it is, but it's only one of the sections, 43 or 44, from the Erwin Kreisig book that I read out loud for you guys last year. Okay, I almost forgot. Really, before I get into this, I'm going to do just a quick speed run review of, I call this a differential geometry equation sheet, but these were like the most important equations, formulas that I used in doing this whole assignment. Because like I said, from my opinionated perspective, after getting the assignment done, it was plug and chug, compute first and second fundamental form coefficients, calculate normal vectors, principal curvatures, Gaussian curvatures, so on. But I think it would be helpful to kind of give like a general broad overview, kind of like a context, a recap of the differential geometry. So the first fundamental form is, the second fundamental form is, the third fundamental form is, and then she said, I don't want to talk to you anymore. Classic. Okay, the first fundamental form is, you could say, an intrinsic metric. Metric meaning, how are we going to measure things in geometry? A lot of geometry is non-quantitative, right? It's very spatial, visual, etc. You just want to say, okay, if you're given, a circle, how do you inscribe that circle in a square? Or if you're given a square, how do you circumscribe that with a circle? Your only tools are going to be a straight edge and a compass, okay? The metric is like the next step for doing calculus on it. You want to do like algebraic things with whatever you've done in geometry, or you want to do particularly infinitesimal algebra or calculus, right, on these things. So that's kind of where the fundamental forms are helpful for that. But there was a lot of a debate historically about, you want to tie these metrics to internal properties of the surface that you're on. You don't want to have it so much dependent upon the global aspects of whatever space it's embedded in, or like global aspects of the surface you're on. Like maybe you don't know for sure if you're on the surface of a torus, or if you're on the surface of a cylinder, or if you're on the surface of a sphere. But you want to come up with these intrinsic definitions to sort of mathematically be able to figure out, disambiguate those kinds of scenarios, right? So that's kind of like the big picture of where people like Gauss and Euler and Riemann, that's where they were all coming from when this stuff was in vogue, you could say. So first fundamental form is wholly intrinsic. It's very useful, like I said, for computing or measuring distances and angles on a given surface embedded in 3D space. Critically 3D space, because like I said, Gauss was capped at doing everything in 3D. He didn't generalize this to n-dimensional space, okay? So we have capital I, or otherwise denoted as d lowercase s squared, that's the first fundamental form, is given by capital E times du squared plus 2 times capital F times du dv plus capital G times dv squared. The key part is the coefficients. So we have capital E here, which is also sometimes denoted, namely like in the Kreisig book, it's denoted as lowercase g sub 1, 1. This whole capital E, capital F, capital G notation is called Euler notation, if I'm not mistaken. But it was mentioned once in the Kreisig book, and then they were like, okay, we're just going to use G sub 1, 1 for capital E. Capital F is going to be G sub 1, 2, and capital G is going to be G sub 2, 2. I kind of like mixed that up if you're reading along on my website right now. But anyway, so the first coefficient of the first fundamental form is the dot product between, you take your parametric vector representation of your surface R, and you do the first derivative with respect to your first coordinate axis, which is in this case u. So you do R is your given vector parametric representation, take the first derivative with respect to u, dot product that with itself. That's how you get the first coefficient of the first fundamental form. Second coefficient of the first fundamental form, similarly, you have your vector parametric representation, take the first derivative with respect to u, start over. You have your vector parametric representation, take the first derivative with respect to the other coordinate axis direction, v, and then you dot product those together, ru dot rv, that's the second coefficient. Third coefficient, surprise. You have your first derivative with respect to your second coordinate direction, v, so you have rv, dot product that with itself. That's how you get the third coefficient of the first fundamental form. On this equation sheet, I denote vectors with bold letters. People do all kinds of crazy things when they want to tell you that it's a vector. The least obnoxious way besides doing bold characters that I've seen is like underline them. So instead of doing like an overbar, do like an underbar. But I think anything besides that is just like really obnoxious. Like if you're multiplying it by unit vectors or something like that, I see a lot of that in physics stuff. It's just like a notation mess. So that's why I go with the bold face characters to denote vectors. So keep that in mind. Okay, so the second fundamental form is arguably the more important the most important fundamental form, and people don't really call it the second fundamental form anymore. It's more generally known as the induced metric. So if you look up in a smooth manifolds book, you'll be like, where's the fundamental forms, right? You'll just see the induced metric in the index, and then when you flip over to that page, it'll just kind of briefly mention, oh yeah, this is also known as the second fundamental form, but no one calls it that anymore. So go figure. And part of that, just my quick take, is that principal curvature is, due to its formulation, proportional to the second fundamental form. So by the time you've calculated your induced metric, you're kind of close on the way to having one of the many different ways of characterizing the curvature of whatever you're trying to find out the curvature for. Okay, so also I should say, the way you get the first, second, and third fundamental forms is, if you think about a surface, it could be a surface embedded in 3D space, for instance, and what's calculus 1 all about? Derivatives. What are derivatives in a geometric interpretation? Tangents. So, there's, like in Calc 3, directional derivatives, and the big problem that you have with the directional derivative is you could be like, well, what direction are you going to be in to define your derivative, right? Because if you're in a 2D plane and you have some plane curve and you take a derivative at some point on the curve, your tangent is unambiguous, essentially. I mean, technically you could have like two definitions. You could take what's perpendicular to like the traditional, everybody knows how to do a Calc 1 derivative, but really there's just one tangent vector that you get when you do a derivative for a 2D plane curve. And then it gets all ambiguous when you're in 3D space and above, so you need to do directional derivatives. Well, as I'll see here at the end of my long-winded equation sheet speed run, the principal directions are a kind of way of not being so ambiguous, but I'm getting ahead of myself. So you have a surface embedded in space. Keep track of all your tangents when you stand in one place. So you have tangents, okay? First fundamental form, take dot products between your tangents. Straight up. That's what you're doing. And then kind of like how I just said, oh yeah, you have a plane curve. You could do your Calc 1 derivative, and then you could say, oh, there's more than one. There isn't a unique tangent, regardless of whatever the, analysis proof begs to differ. You could just be perpendicular, and then technically it only, touches your curve at one point. But then it's really not a tangent in the strict sense of the definition. Okay, but if you're on a surface, then you have tangents and you also have normals. So the second fundamental form is, well, now take the dot product of tangents and normals. And then the third fundamental form is, okay, now take dot products of normals with normals. So first fundamental form, dot product tangents with tangents. Second fundamental form, dot product tangents with normal vectors. Third fundamental form, dot product normals with normals. Okay, so second fundamental form is defined as negative dr dot dn, whatever, but that equals L du squared plus 2m du dv plus n dv squared, where capital L, capital M, and capital N are now the coefficients of the second fundamental form. So capital L is equal to, what is this? Good question. We have the vector parametric representation of our surface, R, and we're going to do a derivative with respect to our first coordinate axis, u, and then we're going to do another derivative with respect to that same coordinate axis direction. So R sub uu here denotes the second derivative of your vector parametric representation of your surface with respect to u each time you took the derivative. Dot product that with your normal vector n, lowercase n, okay, because I recycled the letter capital N, which I'll get to for the third fundamental form. And honestly, I typed it up this morning as I'm reading it now. We have L equals, M equals, and then I didn't put N equals. So anyways, the second coefficient of the second fundamental form is now we're going to take our vector parametric representation, take a derivative with respect to u, and then take another derivative with respect to v. And then we dot product that with the normal vector. And these second coefficients of the fundamental forms are symmetric in that it doesn't matter which derivative you take first, because technically if there were a difference, then you could argue or infer that one of those first derivatives with respect to either coordinate axis where it ended up making a difference which order you did it in, one of those derivatives turned out to be 0. Or, yeah, so that's why these second coefficients of the fundamental forms, you could just say like ruv.n, or you could say rvu.n, and it's the same thing. So anyways, I didn't type in capital N here, but the third one, capital N, the third coefficient of the second fundamental form. You do a derivative of your vector parametric representation with respect to v, that's your first one. Then you do it again, you have a second derivative now. You also do that with respect to the coordinate axis v. So we have rvv.n. And kind of like how there's this whole Euler notation or whatever, the alternative way of writing the coefficients of the second fundamental form, which is used throughout the Kreisig book, is saying b sub 1, 1 for L, b sub 1, 2 for M, and b sub 2, 2 for capital N. And then we have the least heard of, in my opinion, I mean, I haven't really seen a whole lot of the third fundamental form, the least used of the three fundamental forms. It's kind of obscure, and it's hard to track down what the meaning of the third fundamental form is, but really it's taking the first fundamental form of the projection or the image of your given surface onto the unit sphere. So you take your surface, project it onto the unit sphere, and then whatever projection you're left with, you take the first fundamental form of that. So the third fundamental form is dn.dn, where these n's in this case are vectors denoting your normal vector. Kind of like I said, normals dot with normals for this one. And there's no Euler notation as far as I know for this one, but we have the first derivative of our normal vector with respect to u, dot product with itself, and then times du squared plus 2 times. Now we're going to take that normal vector, take a derivative with respect to u, and then dot product that with the normal vector after we take a first derivative with respect to v, the other coordinate axis direction. Take that times du dv, and then plus, surprise, normal vector, take the first derivative with respect to your second or final remaining coordinate axis direction v, dot product that with itself, you get dv squared. So this is kind of like how I was mentioning the different kinds of notation, right? It's kind of helpful to know that the discriminants of the first and second fundamental forms are at least going to be denoted as, without any subscripts, lowercase g. That's the first fundamental form's discriminant, which if you just, draw out the little 2x2 determinant matrix, calculate it out in your head, g sub 1, 1 times g sub 2, 2 minus g sub 1, 2 squared. Same thing for the second fundamental form, the discriminant of the second fundamental form, that is, we have lowercase b equals b sub 1, 1 times b sub 2, 2 minus b sub 1, 2 squared. That's the thing that I can get criticized for in my earlier videos, reading the differential geometry book out loud for, is that basically like right after the sections where the first and second fundamental forms are brought up, we just jump straight into tensors, okay? And then the whole covariant, contravariant, subscript, superscript indices, I was like, what? I was just kind of like reading the solutions to the problems from the back of the book out loud. And I probably didn't read the textbook word for word as well as I could have, in explaining the concepts. But now, after having it swirl around in my mind for all this time and doing all these problems and bringing it to work and all this stuff, it's starting to gel in my mind, so to speak. So those are the discriminants of the first and second fundamental forms. Another useful thing on the equation sheet, normal vector, is take the cross product of, so x here is your vector parametric representation, and you do the derivative with respect to the first coordinate axis. That's what the subscript 1 denotes. Then start over, take the derivative with respect to your other coordinate axis direction. That's what x sub 2 represents. Cross product those together, slap that into a fraction over a denominator of the positive square root of the discriminant of the first fundamental form. That's how you get your normal vector. And then we're getting to the different kinds of curvature. That's kind of one of the main things that differential geometry is trying to be able to calculate, compute, talk about, reason mathematically, is curvature. That's like the big thing. Ricci curvature, Riemann curvature tensor, all that. So if you want to see the Riemann curvature tensor, Ricci scalar curvature, all that stuff, you can go to my website, go to the files section, and read my filling in the gaps of Riemann's habilitation thesis, which is also one of my differential geometry episodes, like episode 34 or something like that. But, tensor contractions and stuff like that, it's kind of brutal, to be honest with you. Just like cranking out the algebra, man. But, okay, so what are principal curvatures? This is kind of what I was talking about with when you're in Calc 3 and you look at directional derivatives and you're like, I don't know which if you don't give me a direction, I can't calculate it all the way through. So if you're on a surface embedded in 3 space, this is how they kind of get around that, is you find the direction at a given point, let's say, where the derivative is the greatest in magnitude. So it could be increasing the greatest or decreasing the greatest. And you take that to be your first so-called principal direction. And then orthogonal to that direction, that's your other principal direction. And then you say, okay, now we're going to compute the curvatures along those directions. Those are the principal curvatures. And as a matter of fact, when you do that, there's a couple scenarios that could happen. 3, basically. You could be Euclidean. It's like a plane at that point where your principal directions are equal to 0. So you're isomorphic to an infinitesimal plane as far as you know at that point. You could also be at an elliptic point. So, it's like basically the way it sounds if you think of being like on the surface of a sphere or something, and you look out at right angles, you have your principal curvatures are both of the same sign. You could be on the inside of the sphere, you could be on the outside of the sphere, but it's the same. The other one is, which is kind of weird to think about, is hyperbolic. So that's, in real life, I always think of it as like being on a Pringle, like one of those chips, where if you're looking at one principal direction, it's kind of like one parabola or curve facing, let's say, like down. You're looking down the slope of the Pringle. And then at a right angle, though, when you look the other way, you're on another parabola and it's looking up, right? So the sign of each of those principal curvatures are opposite to each other. So yeah, hyperbolic, elliptic, parabolic. I think I might have messed that up because parabolic, that doesn't really sound like it's isomorphic to Euclidean. Anyways, we're going to get to the answer that I actually wrote down for problem 6 because I'm more confident that that's correct. But anyways, the way that you calculate these principal curvatures is by using the coefficients of the first and second fundamental forms. So this is, right, like Gauss was trapped in 3D space, so you only have 2 principal curvatures. First principal curvature, we have the first coefficient of the second fundamental form divided by the first coefficient of the first fundamental form. And then for the second principal curvature, you have the third component of the second fundamental form divided by the third component of the first fundamental form. That's kind of a vague way to calculate them. A more direct or just like algebraic crank it out method is to compute the eigenvalues of the Weingarten matrix, which is also called the shape operator. I think that also lends itself to being generalized to higher dimensions than just spaces embedded in 3D space, surfaces embedded in 3D space. But anyways, this Weingarten matrix, capital W, is equal to, take the inverse of the matrix of coefficients of the first fundamental form, and you multiply that by the matrix of coefficients for the second fundamental form. That's how you get the Weingarten matrix. Then you find the eigenvalues for that. So take the determinant W minus lambda times I is the identity matrix, solve for lambda. Anyways, Gaussian, okay, well, before I go any further, so let's say that you've calculated these principal curvatures, okay, and you have a bag full of principal curvatures. You're like, what am I going to do with all this? Well, you basically got 2 options. Option number 1 is multiply them together, and option 2 is add them together. So that's basically what the Gaussian curvature and mean curvature are. Gaussian curvature, straight up, multiply them together. Capital K equals kappa 1 times kappa 2, which turns out is equal to the discriminant of the second fundamental form divided by the discriminant of the first fundamental form. Awesome. But also, Gauss, being the sick individual that he is, did the math, and it turns out that you can formulate Gaussian curvature so that it's only in terms of coefficients of the first fundamental form. So since the first fundamental form is this intrinsic metric where you don't have to know anything about the global blah blah blah, you just know that Gaussian curvature is therefore also an intrinsic property, quantity associated with the mathematical structure of the surface that you're given. So that's multiplying the principal curvatures together. Like I said, we could add them together, but really what it turns out to be is that you do the arithmetic sum. So that's what mean curvature is. Add up all your principal curvatures, and then since you only have 2 because you're in 3D space, so you have 3 minus 1 equals 2 principal curvatures, multiply by 1/2, you've got the average, the mean curvature. And this is kind of like the last thing before I get to the problem solution. The third fundamental form kind of just wraps up the connection between the first, second, and third fundamental forms and Gaussian and mean curvature. And you have this nice Enlightenment era, short little, math. Oh, it's so neat and tidy little formula here. Capital K times the first fundamental form minus 2 times capital H times the second fundamental form plus the third fundamental form equals 0. So Okay, but anyways, getting back to this. So I don't know if I am going to cut it out during editing. The little part where I was talking before I went and forgot that I had the equation sheet speedrun to go over. But when I was reading the statement of this problem, we have a torus and we've imposed coordinate axes u and v. And when I show the little illustration below, I'll show exactly what u and v mean, literally, visually. But when I start the solution here, we have to keep that straight from the coordinate directions of the overall space, which in this case I'm calling x1, x2, x3. So for a torus embedded in 3D space, say x1, x2, x3 space, there will be 3 minus 1 equals 2 principal directions and 2 corresponding principal curvatures. Denote the components of the first fundamental form by g sub jk for j and k equal to 1 and 2 respectively, and the components of the second fundamental form b sub jk for j and k equals 1 and 2 respectively. In this case, the subscripts j or k being 1 corresponds to the coordinate axis direction on the torus u, and likewise, when j or k are equal to 2, that corresponds to the coordinate axis direction of v. So, like I said, plug and chug time. First, compute the first and second derivatives of your vector parametric representation of the torus, vector r, needed for computing the first and second fundamental forms. So, I'm not going to read this out loud, but we have the first derivative of r with respect to u, we have the first derivative of r with respect to v, then we take another derivative of ru with respect to u, we take another derivative of ru with respect to v, and then we take another derivative with respect to v of rv. And it's pretty easy. These are just, sine, cosine, trig derivatives. So if I made any mistakes, comment down below. If I made a mistake in any of this, it may be a missing sign error, like a minus sign that kind of like appears and disappears. Because I wrote this all out by hand and then typed it up. And so probably in doing so, there might be like a sign, ghost, disappear, reappear, missing deal. So let me know if you see anything wrong, or in the rest of this assignment solutions, if you have time to read it, that is. So next, compute the components of the first fundamental form and the discriminant of the first fundamental form using what I just calculated. So the first component of the first fundamental form, derivatives, we do dot products of tangents, ru dot ru. And it turns out that this first component of the first fundamental form is equal to a squared. Tangents dot with tangents. Second component of the first fundamental form, g sub 1, 2, ru dot rv. Turns out it's equal to 0. Third component of the first fundamental form, rv dot rv. Turns out it is equal to quantity capital R plus lowercase a times the cosine of u closed quantity squared. And then subsequently, we have a nice easy computation of the discriminant of the first fundamental form, which is equal to lowercase a squared times the quantity capital R plus lowercase a times the cosine of u closed quantity squared. Next, a little bit more involved to compute the components of the second fundamental form, because if you remember what I just said in the speed run of the equation sheet, you need components of the first and second fundamental forms in order to compute Gaussian and mean curvatures. So first, we're going to compute the normal vector for the torus, starting with the appropriate cross product of first derivatives of r, which I started off my calculations with. So ru cross rv, set it up as this determinant 3 by 3 matrix where the first row is the unit vectors in the coordinate directions of the embedded space. So I, j, and k are the unit coordinate vectors for x1, x2, x3 directions, which are different from the directions u and v on the torus. You just calculate this determinant, and you're going to get a vector out of that because, right, the discriminant of the first fundamental form is a scalar. We want to get the normal vector. So from the definition, we can kind of infer that the numerator here, x1 cross x2, it's going to result in a vector. So there's going to be 3 components that you have to keep track of. And we've got all this cosine u, cosine v, cosine u, sine v, sine u, cosine u all over the top here in the numerator. It's like you got to be really diligent about keeping track of that, especially when you're doing like the trig derivatives, right? Because then that's kind of why I was a little bit afraid that maybe I'm missing a minus sign that then reappears, disappears in the final answer, because it was a sign error. I don't know, but it all works out to just be a vector, 3 entries. The first entry of our normal vector is negative cosine u times cosine v. The second entry is negative cosine u times sine v. The third entry is negative sine u. That's the normal vector. So next, use the previous results to compute the components of the second fundamental form, namely b sub 1, 1 equals the second derivative of r with respect to u each time, dot with the normal vector. B sub 1, 2 is equal to take the derivative of r with respect to u and then v, or v and then u, dot product that with the normal, and the third component of the second fundamental form, rvv dot n. And then subsequently make hopefully an easy calculation for the discriminant of the second fundamental form, just lowercase b. And these are all going to be scalars. So as you can see, I went through, calculated it out. The first component of the second fundamental form in this case is just lowercase a. The second component of the second fundamental form, b sub 1, 2, or in Euler notation, it's capital M, that's equal to 0. And the third component of the second fundamental form, b sub 2, 2, or capital N, kind of confusing with all the normal vectors floating around, but at any rate, that is equal to the quantity, capital R plus lowercase a times cosine u, closed quantity times cosine u. Therefore, the discriminant of the second fundamental form is lowercase a times the quantity capital R plus lowercase a times cosine u, closed quantity times cosine u. And now we have all of the pieces and parts that we need to put together the principal curvatures, Gaussian curvature, and mean curvatures. So first, the principal curvatures, we have kappa 1, which is just b sub 1, 1 over g sub 1, 1. It equals negative 1 over a. For the second principal curvature, we have b sub 2, 2 over g sub 2, 2, which in other words is the third component of the second fundamental form divided by the third component of the first fundamental form. In this case of the torus, with its parametrization given above, is equal to negative of the fraction with a numerator of cosine of u over a denominator of capital R plus lowercase a times cosine u. And now, like I said, we're going to multiply them together and we're going to add them together in order to get the Gaussian curvature and mean curvature. So Gaussian curvature works out to be a fraction with the numerator of cosine u over a denominator of lowercase a times the quantity capital R plus lowercase a times cosine u, closed quantity. And the mean curvature turns out to be equal to negative 1/2 times the quantity of a fraction with a numerator of negative cosine of u over a denominator of capital R plus... My cat's eating his lunch. Plus lowercase a times cosine of u, that's the fraction inside the quantity, which is then minus 1 over lowercase a, closed quantity. So now we have all of our mathematical description, but we're going to toss it back to the right hemisphere of the brain, and we're going to try to seize the context of what's going on here. Okay, we're not just going to be dialed in the left hemisphere, cranking it out. We're going to go back to the right hemisphere and look at the big picture, literally look at pictures here. So if V is equal to positive or negative pi over 2, then Gaussian curvature capital K is equal to 0. That is, circles at the maximum and minimum height, which in this case is lowercase a on the torus, which I'm just going to call the torus capital S, let's say. When I'm referring to the maximum and minimum height here, it's measured from the torus center perpendicular to the radius of the torus, capital R, and these circles consist of parabolic points only. So you can kind of see this in the pictures below if you're already looking at them. I mean, if you're watching this video, what are you going to do? Like, put your hand over the screen or something, or like avert your eyes? I don't know. But there's really only two circles on the torus where there are parabolic points, or where Gaussian curvature is equal to 0. So that's at the top of the torus, and then it's not pictured here, but then it would be at the same below here. So if you drew an axis straight through the whole of the donut, and you're sitting at the center of the torus donut, capital S, and you go bam all the way up to the top height of the torus, that's where parabolic points are. And then you could go bam down to the minimum height, parabolic points, which not shown here, but hopefully you can use your imagination and figure it out. Before I get to the MATLAB, I will say when I first plotted this, I was a little bit skeptical. I was like, that doesn't look like the top of the torus donut here. The next circle out, that black circle that I've got the mouse over right now, I almost, like if I were drawing a picture, I might have drawn that to be the parabolic points curve just from eyeballing it. But it's like, that's why you do the MATLAB, right? So you get it exact. You know what I mean? Anyways, points on the torus, capital S, the surface of the torus, whose distance from the center of the torus to its height extrema along the x3 axis in the figure below is greater than the square root of the quantity capital R squared plus lowercase a squared closed quantity are elliptic, while those whose distance from the origin or center of the torus, capital S, is smaller than the square root of the quantity capital R squared plus lowercase a squared closed quantity are hyperbolic. Okay, what does that mean? So I shaded it in on the illustration. Again, if you are, you've got like a pole going through the center of the donut hole, and you're hanging on for dear life at the center of the torus, then everywhere between the parabolic points that are at the very height of the torus and then the parabolic points that are at the bottom of the torus, all of the inside of the surface of the torus, those are all hyperbolic points. So Gaussian curvature there is negative. And that's what that sentence meant to say. And similarly, everything outside of the torus, between the parabolic points where I shaded it blue, those are elliptic points where Gaussian curvature is positive, greater than 0. And if you're already, losing blood flow to your brain and you don't remember the statement of the problem, it was like, okay, what are the lines of curvature on the torus? And so you kind of guess, okay, well, the parabolic points, you've got these like rings going around the donut here. That's where we're going to have lines of curvature. But also the other half is that perpendicular to those, the other sort of rings, these would all be circles, right? These are the dashed lines that I have on this figure. Those are also lines of curvature. So this is kind of like something that I didn't know when I did this problem, and I got backwards, is which of these lines of curvature are called meridians and which ones are called parallels. because I'm pretty sure I got it backwards. I was like, okay, the solid lines here where we've got constant Gaussian curvature, those I would have called parallels. And I would have called the dashed lines that are going vertically here are meridians. But, okay, reading on here, the curves of constant Gaussian curvature are the meridians. Okay, so that, like I said, I got it backwards. That is to say, the lines of curvature, which as plane curves lie in planes parallel to the x1, x2 plane. Okay, here we go. x1, x2 plane, if you just envision lifting the plane throughout this, then all of the lines of curvature with constant Gaussian curvature are going to be circles embedded in that plane. Okay? But then, kind of like I said, if you had another plane, and to back up a little bit, if you're dragging this x1, x2 plane through your torus donut, then those circles are going to vary in their radius. You're going to have like a small circle when you hit the first set of parabolic points at the minimum of the torus, and then you're going to go all the way up. It's going to get to the maximum, and then it's going to shrink back down until you get to the parabolic points at the top of the torus, and then it's going to disappear. But when you look at the other lines of curvature, you are perpendicular to the torus, I guess you could say, and you're circling around it. And your projection of the torus that whole time is, of course, going to be a constant circle. So if you're circling around the donut with like a visibility plane going around in circles, you're just going to see one circle. But then if you do the whole like flat land is getting haunted by a spiritual paranormal torus donut that's drifting through flatland, then all of the inhabitants of flatland are going to be freaking out when they see this growing and contracting circle that just like appears and disappears, right? If the inhabitants of flatland are in something parallel to the x1, x2 plane. Anyways, note that a second circle consisting of only parabolic points on the underside of the torus at its minimum z-axis height in the left figure below is not visible. Okay, I already said that. And now here is a cross section I kind of just added for visual aid here. I noted in the legend, I'm like, okay, well, this is what I was saying about we've got x1, x2, x3 as our embedded space that the torus donut is living in, okay? These are rectangular Cartesian coordinates. But U and V are coordinate axes that we imposed on the surface of the shape of the torus for the sake of having a vector parametric representation of the torus that we can express algebraically in terms of those variables U and V. So if you look at the cross section, V is if, kind of like how I was saying, you're spinning around the donut and you have this constant circular cross section. Well, if you go to the center of that circular cross section and then go radially along a vector that's going from the center to the edge of that circle, that is V. And then U is radial with respect to the x1, x2 plane, right? So if you put a point at the center of the donut and then you go out to the edge, the very edge, perhaps, of the torus, and then you go radially with that vector, that's the U coordinate axis. And then V is within there. Anyways, and before I get to the MATLAB that produced this, which, I don't know, I'm not really going to say a lot about it. If you want to read the MATLAB, go for it. But it's like, from my point of view, it's a little bit self-explanatory. It's just like calculating exactly what all of this stuff is. Like calculating the region where it's going to be green. And then, if you screwed up this problem, then your MATLAB figure image is going to look like crap. Like you could draw this with like colored pencils or something like that. And then if you go to MATLAB and then you type it in, you're like, woohoo, I think I got this. And then it doesn't look like that. Well, maybe you got the math wrong, right? And by the way, I did use a specific value of capital R and capital A here, but that was just for the sake of visualization, right? Anyways, so you could say, well, I don't know, this could all be wrong, okay? Where's the solution in the back of the book? Well, it turns out this figure right here on the left, I guess you could call it figure 2A, this is on the homepage of that computational geometry course. Of all the pictures that he could have chosen, it was basically the answer to part of problem 6 for assignment 1 here, you could say. So he even shows, okay, capital K equals 0, and he's got a line pointing to, I guess, the green band, and then K being negative on the inside of the torus corresponds to the blue region, and then K being positive, Gaussian curvature being positive, is where it's shades of orange and yellow. And so what do you know? That's what I have. And I think the description also was like, ooh, we also have here lines of curvature of the torus. But I'm like, dude, that is kind of confusing with the like two donuts interlocked as rings together here. So I don't know. And then kind of like how I was saying from the Erwin Kreisig textbook, where the answers are literally exactly what I have here at the bottom of page 7 of my solutions, except everywhere that you see the letter U in the book, it's a letter V, and everywhere where there's a letter V, it's a letter U. So you can kind of maybe glean that from here, because if you use, I don't know, it says U2 here, U1, but anyways, my cat threw up. It's okay, poor guy. Yeah, same thing. Constant Gaussian curvature. K equals 0, we have this line. It's kind of like an implied top-down view. Negative Gaussian curvature, it's on the inside. Positive Gaussian curvature, it's on the outside. And then it's basically the same little cross section as what I have up here. So, yeah, and it turns out it's section 44. And, you know, I tried to be thorough and throw in the scholarly references and do all that, but anywho, let's just go over the MATLAB for the finale. I made 2 scripts. Oh, I'm going to switch this. Oh, it's still on the right side. 2 scripts. One is for the color 3D torus, and then one's for the cross section. So I'm just going to kind of gloss over based upon what I wrote in my header comments. You just draw a torus, give it a white surface, that way it's not just kind of a frame in space, and then shade the regions of positive or negative Gaussian curvature, use the surf function. And then I drew in the lines of curvature, starting with the latitudes, the meridians, solid lines. These are lines of constant Gaussian curvature. Then the dashed lines of curvature, which are of varying Gaussian curvature. Drew the line of constant 0 Gaussian curvature as a red circle on the top. Didn't do it on the bottom because you can't see it. And good habits as a scientist, things that got beaten into me during grad school. You have to title and label your plots, your figures, your axes. You have to add a legend. You have to make it big enough so that other people can read this from the back of the room, and you're presenting this on your PowerPoint slides. So thank goodness that this got beaten into me, because it's a good habit to have of like really trying to make your figures look good, and so that you can convince other scientists, scholars, engineers, blah blah blah, that they're not just going to look at it and have to be like, oh, I need my reading glasses and a magnifying glass, and I can't read it after I print it out on my crappy printer or whatever. So anyways, yeah, and then just real quick, did the cross section, and so all of this is just talk, right? So we want to see some results. I've got the code open right now, and the real test is if I go in and I run this right now, is it going to reproduce the figure that I put on the solutions for the assignment? Boom, there you go. There it is. Title, 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 axes titled, legend, legible. There you go. That's it. See you guys in the next one.